All right, here we are for Honors Physics, Projectile Homework Set Worksheet 2, looking at problem number 6. It says, a football is kicked from the ground with a speed of 23 meters per second at an angle of 42 degrees above the horizontal. How long is the football in the air? So we're solving for a time. And then how far does it travel? Presumably we're going from the ground to the ground, same height to same height. So we're trying to find the horizontal distance that it travels. So this is going to look something like this. There's my grass, right? The field, right? Okay, someone has been taking care of the field. And the football is going to get kicked. Zhunk, zhunk. Laces up. All right. You say, hey, that's going to get kicked with some initial velocity. 23 meters per second at an angle of 42 degrees. 23 meters per second. I'm going to go ahead and recognize that this 23, it's not horizontal velocity. 23 is not the vertical velocity. This is at a diagonal. I'm going to have to replace it with components eventually. So to find the horizontal initial velocity, to find the vertical initial velocity, knowing this angle is 42 degrees. And yes, I'm drawing that really small, sorry. Okay, hey, what is the path going to look like that this is going to follow? Well, I know it's going to, if you start off with this initial vertical speed, gravity is going to be pulling down, making it get slower, slower, slower on its way up, and it's going to keep pulling down, so now it's going to get faster, faster, faster on the way down. It's going to be a nice parabola, like that, okay? Hopefully more symmetric than I drew it there. And so, turns out we're trying to find the time it's in the air. So that would be from here to here. And how far it travels, well, again, that's from here to here. So we're going to solve this problem starting here and ending over here. It's our starting and ending points. Okay. And let's go ahead and fill in, make a chart of table of values and fill in what we know. Horizontal axis, vertical axis. Fill in my chart. A, V naught, V, displacement and time. A, V naught, V, displacement and time. Wonk, wonk. Whoop, whoop. Wonk, 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 wonk. My acceleration in the horizontal axis is always 0 because there are no forces pushing sideways on it. Once it leaves the punter's foot, right? You say, it's only a projectile when the only force acting is gravity. That's just while it's in the air. There's nothing shoving sideways, so the horizontal acceleration will be 0 during its flight. We're not worrying about while it's in contact with the foot. That's not what we're analyzing here. The initial horizontal velocity, that's just going to be this component of this guy. We'll come back to that. Let's go to the other side. The other thing we know automatically for all projectile problems is the acceleration in the y is negative 9.8 meters per second squared because we are near the surface of the Earth. In fact, we're at the surface of the Earth. Running through, what values did they give us? This 23 is not the velocity we want. We want just that horizontal component. So this horizontal side, this is the side that's adjacent to that angle. It's the leg of the triangle that's adjacent to the angle. 23 is the hypotenuse, so we're going to use the cosine function. It will be the hypotenuse times the cosine of the angle. So it'll be 23 cosine 42. I recommend that you draw it right on your sketch like that. And the vertical will be the opposite side of that angle. And 23 is the hypotenuse, so it'll be the hypotenuse times the sine of the angle. It'll be 23 sine 42. I really recommend you write it in right on the sketch right there. Yep. Okay, so now I can copy this down here. Hey, this is 23 cosine 42, 23 sine 42. Now, we're trying to see the time it's in the air. This is what we want to know. We want to know how far it goes sideways. So we are trying to solve for this delta x here to go there, right? All right, looking at this, you say, hey, do I have enough information to solve? And you're like, oh my gosh, this horizontal axis, I only know 2 things. That's not enough. What about the vertical motion? You're like, oh no, I only have 2 things. It's okay. We know more things about this motion. It's just there are things that they're not specifically going to state in the problem. This is a problem where it takes off and it ends at the same height. It turns out there's a ton of special things that we know about projectile problems like this. All right. And so let me go ahead and walk you through all of the special stuff we know about a projectile problem that takes off at an angle and returns to the same height. This is what I call a type 2 projectile problem. All right. So should I run through all that process now or pretend like you already know it? I'll run through it now really quickly. I'm going to give you the full spiel. The full spiel? Holy cow, yes I am. Okay, here we go. Hey, to my mind, when I think about projectile problems, I say that there are 3 types of projectile problems. This is the way that I categorize them in my head. And I find it to be really helpful. Okay, there are 3 types. We know that every projectile problem, we know 2 motion variables. We know that the acceleration in the x-axis is 0. We know the acceleration in the y-axis is -g, which near the surface of the Earth would be -9.8 meters per second squared. Okay, every projectile problem. However, the other 3 types, there are some other variables that we can figure out. As soon as we see from the setup which type it is, there's a bunch of values that we know. So here we go. I call the 3 types, rather unimaginatively, type 1, type 2, and type 3. Okay, a type 1 projectile problem. A type 1 projectile problem is a problem where the projectile takes off horizontally. This is what the projectile type was like in most of the previous problems in this problem set. You say, hey, in problem 1, that projectile took off horizontally. It rolled off the table going sideways. In problem 2, well, that was not a type 2, type 1. In problem 4, a stone was thrown horizontally. And so this is a type 1 type motion. And in problem 5, that bottle was flying horizontally when it was released. And this is a type 1 projectile problem. So those are type 1s, takes off horizontally. We know what those sketches are going to look like. Those are all sketches that are going to look like this. My object begins moving horizontally like this. And so its trajectory is going to be one of these. Right? As soon as you see that this is the setup, you know one of these motion variables. Which one do you know? For a type 1, we know that the initial velocity has no y component. The vertical velocity at the first instant is 0. Okay? They're not going to say that in the problem. It's something you have to just recognize from the situation. Okay, and that's the special thing you know about type 1s. Now, it's pretty nice, actually, knowing that V naught and the y is 0. That means that when you go to do your formulas for the y-axis, V is AT plus V naught, displacement, y-axis, equals V naught T plus 1/2 AT squared, or V squared is V naught squared plus 2A times the displacement. Do you see that V naught being 0 is going to make this term drop out, or this term drop out, or this term drop out? It simplifies your equations really nicely. So type 1s, the math of them is actually not too bad. The other nice thing about a type 1 is because it takes off horizontally and has no vertical part, you don't have to split the starting velocity up into pieces like this, which makes type 1s usually like the first problems you tend to get taught in a physics class, tend to be type 1s. They're just slightly easier than the others. Okay, this takes me to type 2. What makes a type 2 a type 2? As I think I indicated here, a type 2 is a problem where the object takes off and then returns and ends at its original height. That's a type 2 problem. Takes off at an angle and returns to its original height. All right. So what's that going to look like? Well, that's what we just showed here. I'm going to launch it at some upward angle. It's going to follow a trajectory. That's nice and symmetric, hopefully. All right. Maybe we'll put the ground in here. All right. All right. It turns out that when you have a type 2 problem, there are a ton of variables that you're supposed to just recognize. Besides the fact the acceleration of the x is 0, acceleration of the y is negative g, there's a bunch of other things that you automatically know as soon as you see a type 2 setup. So as soon as I see this kind of rainbow here, I'm like, oh my gosh, there's a bunch of stuff, special stuff I'm supposed to remember. So first of all, I'm going to talk about the fact that a spot on this motion that people oftentimes have questions about or you're interested in knowing more about is the highest point in the path here, okay, the peak. A lot of times people want to know information about the peak. So there's a bunch of special things we know about the peak. Well, one thing that's a general fact that is a good thing to know is that for any object, if you show the path that it follows, its velocity is always tangent to its path. So if I looked at this guy when he's here, my path would look like that. It'd be like a line that just touches at this spot. And when I'm here, it's going to look like that. And then when I'm here, it's going to look like that. And then when I'm here, it's going to look like that. So it's always tangent, just touching at that one spot, the curve. I don't know how well I drew my tangents there, but that's the idea. So at the peak, one thing that you notice is which way is the velocity arrow right at the peak? Isn't it like the tangent line would be horizontal? The velocity is horizontal at the peak. So the vertical velocity at the peak, the velocity at the peak, the y component is 0. But there's other things we know about the peak. If we take a look at a graph of the vertical velocity versus time, doesn't this thing start off going upward really quickly? If I split this up, horizontal, vertical, horizontal, vertical, oh, it's all horizontal there, horizontal and vertical, and horizontal and vertical. The horizontal speed stays the same all the way through. Okay, so wonk, 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 wonk. The horizontal velocity is constant. But the vertical speed is going to be getting slower, slower, slower. It's 0 at the peak, and then look what now. Now the vertical velocity is going down. Now it's negative, because I'm, of course, going to treat down as negative. So this graph of vertical velocity versus time, it would start off being a positive value, and then it would become 0, and then it would become a negative value. This graph is going to be shaped like that. By the way, do you remember what the slope of a velocity time graph is? It's the acceleration. It's how quickly the velocity is changing, right? How quickly this is going up or down as time goes by. How quickly velocity is changing. It's my acceleration. And you say, hey, wait a minute. I know the acceleration for a projectile is a constant negative 9.8. It's a constant negative g. So this is a line that has a slope of negative 9.8 or a negative g. Now, there's something else special that we talked about on a previous homework set about velocity time graphs. We talked about the idea that the area between the line and the time axis has a special meaning. Remember what this area between the time axis and the line on a VT graph means? Turns out this is displacement. It's the change in position. You know what this is over here? Between the line and the time axis? That's displacement again. But you see how this area is above the axis? This is going to be a positive value. This area is below the axis. It's going to be a negative value. This is how far it went up. This is how far it goes back down. You say, no, wait a minute. We're supposed to end at the same height. So the total displacement is supposed to be 0. So how far we went up and how far we went down have to balance out. You say, no, wait a minute. This area of this triangle is going to be the same as that triangle. And these triangles, see this line has got the same slope all the way through? So it's the same rise to run ratio. This has to have the same rise to run ratio and have the same area. These triangles are actually going to be congruent. They're going to be congruent triangles, okay, at the same angle. And that means that, check this out, that means this right here, that's when the speed is 0. That's when I'm at the peak. See, positive velocities mean I'm going up. Negative velocities mean I'm going down. To go from positive to negative, I have to pass through 0, don't I? That's why we know that's when you're at the peak. That's when your velocity is 0. That's there. Okay, but the point is, look at this on this graph. This triangle is congruent to this one, and that means wonk, 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 wonk. What's this? This is the time it took to get to the peak. You know what this is? The time it took to get back down from the peak. So the time to the peak is just half of the total time. So I'm saying the time to the peak is half of the total time. Again, subscripts in physics are just labels and tags we can put on things to help tell them apart. All right. Now, wait a minute. If these are congruent triangles, there's something else we can say is equal, and that's this and this. Do you know what those are? This is the velocity at time 0 when I'm here. The vertical velocity, that's this guy. And this, I would read off here with that vertical value. That's the velocity, the vertical velocity at the end. If this was, say, 12 meters per second up, you know what the velocity is here at the end? 12 meters per second down. We can say here at the end that my final velocity in the y component of the final velocity, this guy, is equal but opposite to the initial velocity in the y. Okay, what else do we know? Well, this area, so you say the time to the peak is the same as the time to come back down, right? Because the time to the peak is half the total time. So you say, wait a minute, if I'm trapped, my horizontal velocity is constant. I'm going at a constant horizontal speed, and I do that for a certain amount of time to get to the peak, and I do it for the same amount of time here. This horizontal distance to the peak is the same as this horizontal distance from the peak back to the ground. So I know that my horizontal displacement to the peak is going to be half of my total horizontal displacement. This here is the same as this here. Okay, what else do we know? I'm going from the same height to the same height. What's my total change in height then? 0. So we know our total displacement, if we're going from here to here, the displacement is in the y-axis and the vertical axis is 0. Horizontal is something else, right? But vertical is 0. What else do we know? Well, because, so we kind of said it here, the time to the peak is half the total. I could also say that total time is double the time to the peak. We could say the delta x to the peak is half the total. We could say, likewise, we could say the delta x total is double the delta x to the peak. Yeah, that's kind of silly. What else do we know? We know one more thing. You see how this right triangle for this velocity at the start, this is v naught, by the way. You say the horizontal here, this is my v final, and this horizontal here, they're the same. And this vertical here and this vertical here, we just said by symmetry here, right? Yeah, this velocity and this velocity, these have to be equal but opposite. So whatever that is, that's what this is. So this is a right triangle with these sides, right triangle with the same. These two triangles are the same. This angle here would be the same as this angle here, just negative. Okay, one more thing, and this is neat. If I were to go, I don't know how this color is going to work. If I were to go from the peak and go back some amount of time, and just look at what my velocity is there, right? And I were to go that same length of time forward here, and then measure what that velocity is there. By the symmetry here, right? Those v's are going to be equal and opposite. So for the same number of seconds before the peak and the same number of seconds after the peak. That also means, by the way, this triangle and this triangle would be equal but opposite, which means as I go up and come down, at any particular height, kind of working backwards from the peak in both directions, at that same height, these velocities are going to be equal but opposite. So whatever this v is here, dunk, 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 that's what this vertical speed here is going to be, dunk, dunk, dunk. And this vertical speed here and this vertical speed here. At the same height, those vertical speeds are the same. We talked about that in the free fall unit. And we're just using that same information here. I think this looks very familiar. I think it was worksheet, free fall worksheet problem 3, if I remember right, where I talked about this. So anyway, this is a ton of stuff that you're supposed to just recognize when you see a type 2 setup. Okay, for completeness, let me finish type 3. A type 3 projectile problem. This is one where the projectile takes off at an angle. But ends at a different height than the original. And did I not give myself enough room to squeeze this in here? I can say it real quick. This might be one, a problem like this, where it takes off at an upward angle, and it goes up and then down, right? So it takes off at an angle, ends at a different height. Or it could be a problem where maybe it rolls down a ramp or down an incline and then rolls off. So my object ends up starting off at a downward angle. And then it just kind of goes and curves down. Or it could be one where I launch it upward and then it like give it a shot upward and then it like kind of lands up on a tabletop or up on a mesa or something. These are all what I call type 3s. Takes off at an angle, ends at a different height. Do I know any of these motion variables when I see that I've got a type 3 set up? Well, of course we know the accelerations for all projectile problems. Acceleration in the x is 0, acceleration in the y is negative g. But do we know anything else? Well, in this case and this case, do you see there's a peak? But there isn't really a peak here. It's already on the way down. You know what I mean? So at least for these two, there's a peak. Can I say that the vertical speed at the peak is 0? Well, yeah, that's when it's going from going up to going down, from having positive velocities to having negative velocities. So yeah, that's a peak. So for these particular ones, I could say that the v at the peak is 0. Can I say that for this one? No. So it's not a general thing for type 3s. Will the time to this peak be equal to the time to come back down? No, it's not symmetric, right? Will the delta x to the peak be half the total delta x? No, see, it's not symmetric. It's truncated here, right? So he's like, so that nope. So they're really, other than this, for those, there's nothing else special you can say about a type 3. Now, in a way, it's kind of annoying because it's nice to have these things that are zeros because they help make the equations simpler to solve, right? Make terms drop out and stuff, having these different zeros running around. But it turns out the trade-off is these things with the zeros, there's a bunch of special stuff that you have to remember. This one, not so much to remember, right? And so the math might be harder because won't as many terms drop out. Oftentimes you'll end up, when you go to solve this delta displacement, delta y is v naught t plus 1 f a t squared, if the v naught isn't 0, like it shows up in some of these, this is going to end up having a t squared, a t to the first power, and a t to the 0 power. You're going to end up having to solve a quadratic for time with a type 3. And hopefully you know how to solve a quadratic. Now, I'm not asking you to be able to complete the square and calculate. I'm saying, can you make your calculator solve a quadratic? All right. This is something you need to be able to do for this course. All right. And your math teacher can help you with that, or I can help you with that if you want to know. If you've got one of these TI-84s or similar models, they have built-in solver programs that help that you can punch in and solve a quadratic really quickly. Ask me about it sometime if you want me to show you how to use the solver program, but it really, really is slick. But solving a quadratic is something you'd be able to do. A lot of people program in their own little quadratic solver program too, and that's okay, but there's not a need because there's a built-in function here in the math menu called solver that lets you punch in a quadratic and solve it. It's like, oh. So anyway, once you learn how to use it. Alrighty, that's it. That's the 3 types of projectile problems. It is really helpful to see which type it is, because then you remember that, oh, there's this big laundry list of things I got to know for this one, or this one's just that one thing, or this one I can relax and figure it out. A type 3, because there's not so much you're supposed to just know, that means they have to come out and tell you more of these values. And that actually makes type 3s, in a way, easier to solve and not as tricky. It's just the math sometimes gets rougher. Okay, now that we've done that, wasn't expecting that to happen. We can get back to problem number 6. Wow, that was a long aside. Here we go. Hey, football is kicked from the ground at the speed of 23 meters per second, 42 degrees above. That's right. Same height to same height. This is a type 2. You say, what else do we know then if we're going from here to here? You say, oh, I remember. Look, same height to same height. There's a whole list of stuff we know. We know that the final vertical speed, when it comes and it strikes down here at the ground, it's going to be going like this. And I could split this up. And remember, the horizontal speed is always the same throughout the problem. But the same height here, the vertical speeds are equal, but opposite. So if this was 23 sine 42, here we'll be going down. It'll be a negative 23 sine 42 meters per second. Delta y, what's the change in height? If I go from here to here, they're at the same height. The change in height is 0. You say, oh my gosh, I went from not having enough information to having even extra, more than I need. Look at that, I have everything for the y except time. I better be able to solve for t. I have my choice in the y-axis. I could solve using, and the x-axis, of course, we're always going to use displacement is velocity times time because it's constant velocity. We're trying to find the delta x. We're trying to find the t. We don't know either of those yet, but we're going to find the t right here in the y-axis. We could use either equation that has t because we have all these other variables. I think that this is the nicest one to use. A is v is at plus v naught. Trying to find that t, that would be t is v minus v naught over a. Substitute in my values. Negative. By the way, look, v is negative 23, v naught is 23. Are these going to cancel out? No, because that negative sign. I'm going to have negative 23 sine 42. That's my final velocity, minus, from the equation, a positive 23 sine 42. That's just going to be double negative 23 sine 42. Do you see that? So it'll be like a negative 46 sine of 42 degrees. Make sense? That's my time. Plug it in my calculator, And I will get negative 46 sine 42 degrees. I'll get a negative. Oh, I got to divide by the acceleration. The acceleration is negative 9.8. Okay, good. Phew! Those negatives are going to cancel each other out. And so I'll get negative 9, negative 9.8. And I will get the time to be a positive 3.14 seconds. So that's my time that it took it to hit the ground. And that is one of the things that I was trying to solve for. How long is football in the air? Now I want to find how far it travels horizontally. So now I'm going to come over here. I'm going to take this time, substitute it in there for t. How far it goes horizontally is its horizontal velocity, 23 cosine 42, times the time, multiply by the time, which is 3.14. Punch that in my calculator, 3.14 times 23 cosine 42, and I get a horizontal displacement of 53.7 meters. I'm going to round it off to that. Ta-da! And that is problem 6. Okay. Along the way, we went ahead and derived a whole bunch of special stuff that you need to know about projectile problems. This was a very, very important problem to go through. All right.